Tonight's tinkering is accompanied by Juice the Oats Oatmeal Stout from Oxus Brewing Company in Winnipeg. I've had this one many times before. They describe it as an easy-drinking dark ale with coffee and chocolate aromas and a smooth body. And it pours with a pretty nice head. So tonight I am looking at this time-of-flight distance sensor that I got in a recent mailbag. It's just a tiny little thing. It claims to be good for distances up to about 4 meters. And it was fairly inexpensive, and I'm interested to compare it to these common ultrasonic distance sensors that usually come in, a lot of Arduino starter kits and whatnot. You can, of course, get them separately. They also come in, or are good in various robot kits and stuff like that. They're a little bit less expensive, but well, I'm going to play with the two of them side by side and just see how they work. But I am going to focus more on this guy because I haven't played with him before. This sensor is a VL53L1X. Feel free to freeze frame if you want and read the whole data sheet. I'm not going to read out all 35 pages of it. I'm just going to go through the highlights. So it uses a 940 nanometer non-visible laser. It is accurate up to 400 centimeters distance. And it runs on a nominal 2.8 volt power supply. However, that is just the raw chip. The module itself claims to be happy on between 3 and 5 volts. And there are different variants on this one you can get. But again, this is the one that I got, the one that can go up to 4 meters. There's a block diagram. And there's a bit of an example schematic. So you have 4 pull-up resistors. There is the host microcontroller, which in my case is going to be an Arduino. And maybe a Pi Pico if I can get that running. We'll try it. And then just a very small component count surrounding the thing. Although I guess to get to 5 volts, there's probably a regulator on the board too. I'll have to look. So even though it claims 4 meters, their tests maximum distance in a dark room say that you should expect accuracy up to 3.6 meters. I don't know that I want to set up a full firing range and test it over its entire length, but for the kind of purposes that we'd use this thing for, I think probably 2 or 3 meters is going to be good enough to know that your robot or your project's going to crash into something or something's approaching and you have to react to it or something like that. But yeah, play with it a little bit. Well, maybe before we do that, let's just take a look at the back of the board and see what we can find here. There is a 3-pin device there, which could be a regulator. So a 6-pin device there. That is a pack of 4 10K resistors, so that'll be the pull-ups that we saw. And then just a couple of capacitors and a couple of resistors. So the 3-pin device is labeled 54FK. That 6-pin says 702 and then some kind of a squiggle sideways. I think before I throw this onto a breadboard, let's just find out what those guys are, just for curiosity. Okay, yeah, that 54FK is in fact a low dropout voltage regulator. Let's see what that data sheet says. Hard to read. Okay. But that's okay. Voltage in 4.3 volts, voltage out 3.3 volts. All right. So it is a 3-volt regulator. And as far as I can tell, that 702 marked device is a dual MOSFET. So we'll just plug it into this Arduino Nano. Could have used any Arduino, but I like to use these ones for this kind of stuff because they are tiny and fit on a breadboard. So I guess we're going to need some code for that too. Searching around finds a bunch of different tutorials. One of the most complete one that I found was from Adafruit, so let's use this one. Plus Adafruit has their own library, so we'll install that in the Arduino IDE and wire it up. They want it wired up to all of the pins, so that's what I have done. You install the library just like you do with any Arduino library. This isn't really an Arduino tutorial that I'm doing, but I'll put a link to this down below if you want to follow it yourself. And then we load up the code, and we'll just take a look at it here. IRQ pin, that is one of the pins that comes off the module. It is the module sending out an interrupt request to the board. I don't think it's necessary, but I'm going to hook it up anyway. And then the X shut pin is the other pin that's on there in addition to the SCL and SDA and power. And that is to tell the module to shut itself down, which the pull-up resistor keeps it alive if you're not doing anything else to it. So I'm assuming that Adafruit's library handles those things. And again, this isn't going to be a code tutorial because, as I have mentioned many times in the past, I am really bad at coding. It confuses me. I'm just going to stick mostly to the hardware. This script mainly just references stuff in the library, which is fine, and prints stuff out. It tests to make sure it works. Yeah, all that kind of good stuff. Anyways, let's load it up and see what happens. So connecting, and I guess I'll measure the distance to my herd of cats back there. And I think the camera will pick it up. Yeah, there you go. It's transmitting some data. Okay, let's see what the serial monitor has to say. So that is saying that I think it's my cats are about 180 to 190 millimeters away. Well, let me just put something bigger back there for that to crash into. All right, so I got this circuit board here at the very back edge of my mat, and the grid on here is in centimeters, so that is the 0 line. The midpoint line right here is 14 centimeters, so we'll just line the front of that up there. I'm not quite sure where the plane of detection is, but I'm going to guess it's the surface of the board, so I'll put that right there. So that should be 14 centimeters. And according to the sensor, it's between 14 and 15. Let me just move it a little bit closer. So there's what it is saying is 14 centimeters, which is about 13. Okay, well that's fairly close. Let's back this off here. So that is the full 28 that my board is, from back here to up there. 27, and that's very, very close actually. That's within 5 millimeters, which is pretty good for something like this. Okay, definitely close enough for a hobby project. I like that. Just for fun, let's compare it against one of these guys, just see how close that is. And again, I don't know exactly what the plane is. I think it looks sort of like the plane of measurement will be right in around the middle of that, so we'll take that into account. And the ultrasonic, of course, needs a little bit different code. This is just an example code that I found from somewhere. It's fairly simple, but let's see. Oh, 14, 13 centimeters. Okay. And that is with this sitting very close to where I thought it would be. That's with the front face of it at 14 centimeters. So, okay. It doesn't have the millimeter precision, but that's probably close enough for hobby work, definitely. Let's back it up to 28 millimeter or 28 centimeters and see what it has to say. And again, that is fairly close. And just back it up a little bit more. There it is. So that's, again, maybe half a centimeter to a centimeter off. That's also pretty close. Although these ultrasonic sensors do have a fairly wide dispersion on them. They are not as focused as a laser beam, obviously, but they still do the job. That's pretty cool. So let us now try it with a Pi Pico, just for completeness. This is a 3.3 volt device rather than a 5 volt device. Let's go searching and see if we can find any information about how to get that thing to talk to it. Again, I'm not going to come up with my own code. I'm not going to modify example code right now because that's not what this is about. I am just experimenting with this module and seeing what I can make it do. And yeah, just seeing how versatile it is. So let's go see what we can find for that. A quick search finds this tutorial from Core Electronics from last year. So let's see what we've got here. They are using proprietary modules. Okay. But they have a couple libraries and some code here. So I'll quickly download those and drop them into Thonny and see what I can come up with here. Give me a minute. All right, so I pulled down that code and I'm just scanning through it to see what pins to use. SCL and SDA, obviously, but it's defining those on pins 8 and 9. All right, so I'll hook that up on my breadboard and load these 3 bits of code in. There is the main. All it's doing is doing library calls. That is the unified library of some sort, and there is the actual library for this VL53 L1X, but it seems to be working at a fairly low level in hex, so I am not going to even try and break my brain on that stuff. Hang on here. Okay, so the SCO and SDA are on 8 and 9. GPIO 8 and 9. This is one annoyance that I have with the Pi Pico, is that the pins are all labeled on the underside. So I'm just using this for reference, and pins 8 and 9 are down there. 1, 2, 3, 4, 5, 6, 7, 8, 10, they're 11 and 12. Right. I'll just have to double check that quickly, but I'm pretty sure that's right. Yeah, I just double checked and those are the right pins, so we'll give it some power here. Put it again right at our midpoint, which should be 14 centimeters or 140 millimeters from that guy back there. So now with those files dragged over into the Pi Pico and it restarted, if we run this, there we go, we get some distances. 175 millimeters, which should be about 140. Let's slide that closer. That is calling itself about 140, but in reality, that is about 4 centimeters closer. So, it's like there's something in the math that's not quite right on there. Let's just back this up to the full 28 at the back of my board here. Back about there. That's closer. That's about 10 centimeters further. There's 28. Oh no, only 2 centimeters off. So it's getting more accurate the further back we get. Okay, let's try something a little bit different. I've got my tape measure set up here. The ceiling is up there. So this is 1 meter and 20. This is 1 meter and 30. Let's see what happens if we do this. That's 1 meter 30. 1350 millimeters. That's close. There is where it's saying 1 meter 30, and that is 1 meter and 25. So not horrible, I guess. You wouldn't want to use it for anything mission critical, but for hobby stuff, that's not too bad, I don't think. Although I think the Arduino was closer than that, wasn't it? Hang on. Let me just quickly switch this back onto the Arduino that we were using it on earlier and see what that does. So now let's hold this at about 1 meter 30 centimeters. And again, 1345 millimeters. Try and get right to where it says that's about there. That's 128. So 1 meter 28 centimeters. That's not bad. That's actually closer than when we're using the Raspberry Pi. I hope you could actually read that backlit tape measure that I was using there. But yeah, that is kind of neat. It's almost as accurate as this thing is. Weird that it has got different accuracy on the two different microcontrollers. Could that be just a difference in the code? I'm not sure. I'm not going to dig into the code because I am just so underqualified for doing that. There will be links to all those tutorials and code that I found down below if anybody wants to dig closer into it. Might also be the voltage, because this one is 3.3 volts and it's supplying 3.3 volts through that low dropout regulator. This one is supplying 5 volts to the regulator, which is taking it down to 3.3 volts. So maybe that's the difference. I'm not sure. Anyway, it is nice to have an additional sensor to add to my arsenal. It's a lot physically smaller than these guys. It's got a narrower field of view, but other than that, it does the same job. Slightly different price point, not too much different, but definitely something worth keeping in the toolkit. Oh, I hope that was informative or entertaining or enjoyable or something for you guys. Questions or comments down below as usual. Oh, talk to you later.